Okay, so welcome. So today we'll be finishing up the lecture on perception and then start with data. We'll see how far we'll get. But before I do that, I wanted to share with you the results of your survey. So about 70% of you guys, there's about 100 students in the class and 70 filled out the survey, so it means that 70% actually did homework 0. But yeah, so we really like to have this information just for our records and also to understand what you guys are trying to achieve in this class and what your backgrounds are. And so I'm going to show you simply the Google spreadsheet analysis of this, and then we'll see some visualization challenges right away here. So these are what degrees your primary concentrations are. There's a lot of computer scientists, about 40%, and then there is 17% computer scientists who don't capitalize their computer science. So clearly that's a data pre-processing wrangling issue. Then we have 2 people here in the big data certificate, 4 people in biomedical informatics, computational narratives, computer engineering, computer science, again a data cleanup issues with a database focus. Then computing, data management and analysis, data science, ECE, information systems, neuroscience, physics, School of Computing, statistics, biomedical informatics in without capitalization, one more computer science with a typo, probably. Then computing, not capitalized, and math. So this is the distribution of your degree. There's not so many secondary concentrations, I guess, because most people here are master students. As you can see here, there's 11 undergraduates. There's 36 graduate students in the MS program. There's 17 graduate students in the PhD program, 8 data certificate people, and then 1 exchange student. In terms of tracks, the vast majority is in the computer science track. The second biggest one is the data track with 30%. I was surprised, I was guessing this is bigger. Graphics and visualization is 4, human-centered computing, the new track there's 2, and imaging and computing image analysis is 1. I'm not going to show you the emails. The map thing, I tried to do a map on Google Maps, but this simply takes ages to work. This doesn't really work, so Google Docs is not really great with maps. It used to be better a couple of years ago, so yeah, anyways. What else? Most, 98.6% own a laptop, which is good. Then we see that Windows XP has finally died a death. So nobody is actually using it anymore. Windows Vista, I think, was dead before Windows XP. Even Windows 7 is rare, majority of Windows users are on Windows 10, and then we have 40% Mac users, and then surprisingly high number of Linux, Unix users with 30%. 1 Chrome OS person. Majority here has been programming over 3 years, so more than 60%, and most of the rest have been programming 1 to 3 years, and then there's a couple of people who have been programming less than that. Less than half, but still the majority, write code weekly. Then we have about 38% who write code daily, and then 2 or more times per month, and then we have a couple of less frequent ones. Primary programming language was interesting for me. So there is a big Python fraction, which is not surprising. And there's a big Java fraction. I guess those are the 2 languages. Java is probably from teaching, and Python is probably for any data science applications. And there's a couple of C++ people, SQL as primary programming language, Visual Basic, C, and then JavaScript for 6 here. And then there's a wide range of programming languages that people know. You can see that Java is still the most understood language. HTML is also pretty popular. Then here we have JavaScript, which also like a majority of people know, Python, SQL, and then there's the more esoteric down here, which is surprising for me is the low number of people who know R, but okay, that's fine, we won't be needing it. And C and C++ are still going strong. So, comfortable with programming, the majority here is pretty comfortable with programming, like around 4. If we're talking about design, we have a little bit more of a skewed distribution. There's very few people who, or this is actually Git, sorry. So we have a little bit more skewed for Git, but you can see that most people are somewhat familiar with Git. So maybe there is not a need for me to do the Git introduction in the future. And then in design, we have like a more even distribution where very few people actually consider themselves to be excellent designers. And in terms of gender, it's 74% male, and then either like 22% or 23% female, and some people didn't want to disclose. And then as age-wise, we have like the classical grad student age, 25 to 44 is the majority. Like here we have probably our undergrads, or very young grad students, and then here like a couple of older people. So that's the statistics about the course. Any questions about that? Any comments? Great, so let's talk about perception today. So the next thing that I wanted to talk about, like remember when we talked about perception, we were talking about all of these factors that influence how we perceive our environment, that we don't not necessarily like see everything like a camera, but instead we have like this like narrow field of sharp vision, and we kind of like do this mental construction of images. So we essentially scan, we have fixations and saccades between them to build an image up. And then we also discussed a lot that our preconceived notions of how the world looks like influence a lot what we perceive. So we are, for example, used to see rectangular rooms. We are used to interpret lighting and shading in a natural way, and therefore it's, for example, really hard for us to see similar or identical colors under different lighting conditions. Now I wanted to introduce you to a concept that's called pop-out, or also pre-attentive processing. So what's the idea here? So pop-out are properties that are detected by the low-level visual system very rapidly, like within 200 to 250 milliseconds, very accurately, and they're processed in parallel. It's called pre-attentive processing because it happens before focused attention, so I don't really have to think about what is there. I will still see and recognize it. And attention is also very important for cognition. What's also interesting about pop-out is that it's independent of the number of distractors. So let me just show you what I mean by that. So here we have like one dot that has a different hue than the other dots, and all of you immediately recognize there's this one dot. You didn't have to think about it, you didn't have to look at each of these dots individually and think about is it red or not. So you saw this immediately. Compared to on this side, there's no such, and you also could tell the absence of such a different stimuli in this other case. This battery is dead. So the opposite of this would be sequential search. So if you have to go through the whole image and manually recognize or like consciously recognize what does it mean. So one example for sequential search is if you're looking for a specific word that is like of average length and of average appearance in a page of text. You essentially have to scan through the whole page. It doesn't pop out. There's other pop-out effects. Here we have a difference in curvature form. Like you can spot the layout, so most people should be able to see that fairly quickly. Here's one circle in these distractors or squares. It's not as fast, so hue is better. And so we'll do a little exercise. I'll be showing a couple of those examples to you with different variables, and whenever you see the odd element, you clap. Okay? Let's try this for. Okay, good. Okay, so the point here is that this is something that works in isolation but not in combination. I can say, like, I have a red pop-out on a blue background, or I have a circle in a sea of squares, but a red circle in a sea of red squares and blue circles doesn't work. So you cannot like use pop-out arbitrarily. You have to always make sure of what are the other distractors. So it's not valid for combinations. We have these conjunctive targets, and so they're not a unique visual property. So generally, here are some other preattentive properties, which some of them I just showed. There's orientation, there's length, there's closure, there's size, there's curvature, there's density, there's hue, there is, this is just supposed to be value. Then here we have flicker. That's not at the give, isn't really working well. And then here we have direction of motion. These are all preattentive properties with different like strength and how and can be therefore recognized at different speeds. And so what are the tasks that you can actually do with this? Target detection is what we just did, so you found the odd one out. You can also have like boundary detection if you have a group of elements that are different from the other ones. You can do region tracking if this is moving. Think of a flock of birds flying around. You are also pretty good at counting and estimating the number of elements that are different. So you can very quickly recognize this is 1, these are 5, or these like 50% or something like that. So this is very easy to do with these properties. So here's a number estimation. So you should have a sense very quickly. This is like 7 to 10 elements. Here the boundaries are very obvious. And again, for conjunctions, the boundaries, they don't really work. Like here we have, here is a boundary of red squares and blue circles in here. And then on the left we have blue squares and red circles. And so that boundary is basically not easy to detect. So there is also a hierarchy of preattentive features. As you already know by now that hue is like a strong one, then hue dominates shape here. So we don't necessarily group by shape. This here works fine in this conjunction, but it's not as efficient as this one here. And here, just looking at the shapes, that is again a fine example. There's more example online that you can look up at this website. There's a couple of theories, and it's not, like psychologists are still not quite sure of how it works. Also, the word preattentive processing is not completely uncontroversial, so that's why I prefer to actually call it pop-out. So why do we need that for visualization? Well, it can be used to draw attention to areas of interest. So like your Facebook status flag, like a status update or a message or something like that exactly uses that effect. It simply shows you something that is very different from its environment, like a red signal, and therefore draws your attention to that particular thing. So if you want to notify a user in some way, this is a way to do it. It can also be used to express similarity or group memberships. I'll be talking more about that. But one thing that you have to be aware is that these visual features have to be very carefully designed. So as you saw with all these distractor examples and so on, it doesn't work in many cases. And this is one of the reasons, for example, why when I design a visualization, I try to absolutely limit color usage in the visualization and then use color for highlighting to essentially be able to utilize this pop-out effect. So that's what I wanted to say about pop-up. The next thing I wanted to highlight is change blindness. This is again a couple of interesting illusions that we're usually not super aware of. So since our attention is not, like we cannot pay attention to everything that is going on in a scene that we perceive. So we cannot also keep track of what is going on. We cannot remember the details of an image across separate scenes, except in an area of focused attention. So for example, if I look at one person right here, and this person moves around, I will certainly recognize it. But if somebody else in this class moves around, or movement is like a strong visual cue, evolutionary, because it's predators moved towards us. But if something else, like color changes or so, it's really hard to see that. And interruption, like looking away or blinking, like emphasizes this effect. This is not really a failure of the vision system, it's more of like inappropriate attention guidance. So I have a couple of images here, and then something significant is changing. Like these are blinking here, And something significant is changing between those two instances. And raise your hand if you notice what is going on, like what is different. We're like at 30% of the class. Or 50%, I heard it already. So take a look at the shadow there's no shadow for the helicopter in one of the images. Here's another example. Raise your hand if you notice what is different. 3 people. It's a pretty dominant feature. So we're like at 15 people. Okay. So without the distractor, it's obvious to see, right? But like this big box here, if this boy, for example, were to appear and disappear, you would immediately recognize it because we are trained to essentially look for humans, for faces, and so on in a picture. But this is something that is essentially background. And if you remember the eye tracking video that I showed, that people pay attention to faces and to humans. They don't pay attention to their surrounding as much. Here's another example. Raise your hand again. So here's a video of something being removed from the scene. And like this plays for a couple of seconds, 10 more seconds. And it's going to repeat. So now it's over. The repeat is not great. So who noticed something change? What changed? Yeah, like a part of the grass here. Like notice, look at the lower, at this corner here. Who noticed something? 3 or 4 people. A stone changed, yeah. The one right here. This one. So, very nice scene. Who noticed the change? Running it again. Who noticed the change? Very few people. So look at this lady's like sweater's color. So these are gradual changes, and so what does it tell us for visualization, right? If we're subtle about making a change that we want somebody to notice, it's probably not a good approach. People might not even notice. And these like videos are all from psychology research papers. Just pay attention and tell me if you notice anything weird. The shirt is different? There's 2 different actors with different clothing. So they both have a similar hair color and both are wearing glasses, but that's something that's called change blindness. Then here, like, the same thing is, of course, like, this is a problem of attention blindness. This was one of the videos already for that. Here is another very entertaining one. Oh, this is again something where I need audio.
Somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, son.
I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you? Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, son.
I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So like this campaign, like you're supposed to look out for cyclists. Here's another video.
This is an awareness test. How many passes does the team in white make?
Go!
The answer is 13. But did you see the moonwalking band?
So this is of the same campaign for watching out for cyclists. Okay, so what are the take-home points? Why am I showing this to like a group of computer scientists in a visualization class? Well, it's the fact that we need to find meaning in what we see. We must selectively pay attention to what is important. And that our low-level vision is very often driven by object features like edges and so on, rather than a conscious effort where to look. Like preattentive processing is a good example of this. And also that our attention is driven by pre-existing knowledge, expectations. So for example, expectations is you're trying to count the number of passes. And so you're not paying attention to the bear. And goals that are stored in long-term memory. And so how does it apply for visualization? Well, I think I've said this a couple of times. We have to take those things into consideration. We cannot expect people to pay attention to every change that we make in a user interface and so on. Okay, so now I want to move on to Gestalt principles. This is Gestalt principles are like a pretty old concept from psychology that was developed by a Viennese school of psychologists led by Wertheimer in 1923, and there's also a couple of recent extensions about them. And so what the Gestalt principles, the theories that these people developed, they very correctly described what they observed, but the underlying reasons for why that is like that is still not completely solved, but even this group got most of them wrong. So what are Gestalt principles? These are like patterns that transcend the visual stimuli that produce them. So here are a couple of examples. A connecting contour and a closing contour, a common color region, a common texture region, proximity for grouping, alignment, or common movement. So these are things that, for example, tell us something about relationships. So here are a couple of examples for proximity. In this example here, the top one, we actually see this as columns, just because the points are close to each other. Down here we see it as rows, just because the points are close to each other in row-wise. That we can see here that color is actually not as strong a grouping principle as proximity, right? We, mentally, everybody would agree that this here are two groups, and we don't group black over orange. So we kind of notice that there is a hierarchy of features. So how can we use that in visualization? We can group things or link them and kind of express a relationship by placing entities in close proximity. That's, for example, what we do when we do plots of multidimensional scaling. We can express similarity by color. And so here we have a couple of simple examples. But more generally, we can essentially co-modulate a channel, something like color, shape, size, value, orientation, or texture. Or add a glyph, add a label, add a frame, and background. So here we have classic pop-out ones, and here we have a glyph. And so here we're expressing that those two elements have something in common. I already mentioned this, but I'm going to reiterate it. There's a couple of perception issues with color. We have the preattentive properties are good for 1 to 2 simultaneous colors, but we need serial search for more. So if I ask you to spot the red dots here, it will take you a lot more time than if I ask you to spot the red dots here. This is of course slower in a cluttered environment. So here there's a couple of highlights on top of 2 windows. This is actually from my research, and I'll share more about this. And what we're trying to do here is to identify all of the highlighted areas. And so we can see that here's one, here's one, here's one. That's pretty easy because it's on a white background over text. Here's one that is also not too hard because of the background. But then right here is also one. And that is rather small, and it doesn't pop out because of the background as much. We can change similarity by showing similarity by modulating everything else, right? You might have seen, I think Windows 7 used the security warnings. They were a pop-up, but they also grayed out the rest of the screen. So this is the darkening approach here. Or you could blur everything else and only keep the elements that you want to show in focus. So here's an example from research papers that do that. So here, these research want to highlight most users press on this button at this point in time. And so they do that by essentially graying out everything else. And here these people wanted to show that you could use blurriness or non-blurriness as a method to selection. A general recommendations for this is don't use this unless your sole objective is to guide the attention towards a single set of items. So if you kind of need people to also understand the context, or if you might be wrong with maybe most people actually don't care about that, then you shouldn't use these kinds of approaches. So I'm going to do a little experiment again with you guys. Well, grouping by proximity, which elements belong together? Clearly those two and those two, right? Color, also pretty obvious. Size, again pretty obvious. Shape, pretty obvious. What about now? So all of these, this kind of shows you this hierarchy of the features. Connectedness, these explicit links, they override what we perceive as belonging together. Even if those elements here are close together, we perceive those as to belong together. This is overrides proximity, overrides color, overrides size, and overrides shape. You can do that in various ways. There's this connectedness is like just a line, but it could also be something like common region, like a common surface, a common outline, a common volume. So all of these are possible. Here's an example of how you can use that in visualization. So here, these are two different clustering algorithms run on the same data set. And what we're trying to show is the relationship between the elements in one clustering and one cluster to another cluster. And we use here these bands to connect between them to show the relationships between them. And so this connectedness here overrides position. You can also do that like with the other one that you could do is enclosure, and here we perceive the enclosure as even stronger. So we have similarity of objects, we have the connection, and then here we have enclosure, so we have this hierarchy. This is actually from one of the readings that I gave for this lecture. Here is another example. This enclosure in practice, you can use enclosure to highlight something that you care about, and you tell like these points, they have something in common. This is what we want to group. Here are a couple of varieties of connectedness used in real life visualization applications. So this is all the same data set. These are all like different hotels, restaurants, or other locations. I think in never mind, I don't remember the city. But you can see that there's like, here's a common region, and these are two variations of lines. These lines here are continuous. These lines have branches. There's actually studies on which of those is the most efficient one, but these differences are pretty subtle, so it doesn't really matter too much which of those you choose. They're all pretty strong. What do you see here? A circle and a square, right? Everybody would assume that this here like continues just like this. So we would not expect like these three cases. None of you probably had a mental image of these three cases, but you couldn't know. There is an occlusion happening here, right? So this is like absolutely possible. So equally well, those are possible. But in our mind, this is like one of the important Gestalt principles. We assume continuity. So we assume that for something that is not obvious, that is not visible, there is a good continuation of the previous shape. So if we have something like this, for example, a curve intersecting here, we expect this case here, we never would expect that the actual shapes are like that. And that's here's like a simple argument of where you could improve a visualization by using like continuous lines instead of orthogonal edges in a node link diagram to essentially disambiguate these cases. So like here, for example, we have this line going down here. It's not 100% obvious. We still like assume it goes straight here, but it's not unambiguous whether it's not taking a right turn here, for example. Here's again from the same paper an example of like two different versions of this tool, where one we experimented with continuity and the other one we actually had discontinuous lines. So here we essentially this is a grouping per cluster, and then we connected this to one big point here, and then had discontinuous continuations here. And it turns out that the continuous version is very simple to do, but the continuous version produces much better results. Closure also applies to shapes that we're aware of. This is a little bit related to these emergence images that we showed. There's no line here that indicates that here the head of this panda ends, or there is no contour for this shoe here. But we still see it like that, right? We still essentially there's no ambiguity for us in our head that this is a closed surface. We can also take this a little bit to the extreme, and only by showing these very simple outlines we have a very good mental image of what we want to represent here. Symmetry is also another Gestalt principle. It's easy for us to spot symmetry. It's like we don't really perceive this as a figure, we do perceive this as a figure, and we equally perceive this as a figure. And here we have the same example that's both related to symmetry and continuation. Here we would assume this to be like a cross and not this kind of shape. So we would assume this to be symmetric. how can we use this in visualization? So for example, if you want to show some subtle differences between two populations, like here, this is a classical population pyramid, where you have the men in blue, the women in red. You can very easily spot there any differences that there are in symmetry. So there's, for example, like a bigger indentation around here for men. It's pretty simple for us to spot. And then we have this tilt up there so women tend to live longer. Again, easier to spot using symmetry. Here are a couple of MC Escher pictures where there is some ambiguity between figure and ground. So here we can see both a cup or two faces, depending on how we interpret the picture. And we can actually switch between them. And here we have like a spectrum from geese to fish that are kind of interleaved between them. So here it's not quite so obvious what the figure and the ground is. So let me give you an example, and I've shown this before for an application of this Gestalt principle in visualization. This is a paper that I wrote with colleagues in 2011, and what we're trying to do is show these relationships, these connectedness for search terms. Like just imagine you're trying to search something in a text editor, but it's a little bit more interesting, not just like by text, but by some semantics. And then we would have like something like this. And so here we could essentially blur everything else. And we see here is like one search term, here is one search term. I mentioned this one before up here, and then here it's really hard to spot. So that would be one option. Another option would be making everything dark. Here would be an option of making everything like highlighted with color. Again, that works quite well except for like this case here. Then you could make it blink. It's not an actual recommendation for visualization systems because it's pretty annoying usually. Or we could draw, you could use connectedness. And so in this particular paper we evaluated what is the most efficient visual encoding, and it turned out that connectedness is very efficient, that people actually never miss a region. One problem though is that you have these occlusions here if you draw lines like this. And so what we did is we developed an algorithm that routed around common regions. And so you can see that these links, they try to occlude as little as possible. There's basically no text occlusion. Okay. So the takeaways from this part of the lecture is knowing about perception is important for visualization and UI design. You need to know how to properly choose your color, how you want to show relationship, how to draw attention to something you care about, and how to minimize the risk of your user overlooking something. Great, so this concludes the perception lecture. Now, I wanted to do a design critique. Use your computer to go to this website and you'll find this document. There's an interactive video. I'll be showing the video, like a video in a second. Okay, so this is a tool that was actually also published in the visualization conference, and I think it's pretty cool. I really like the idea behind it, and here's a video.
Hi, I'm Michael Abdallah, creator of CodeSwarm. This video is meant to be a companion to our paper, so it assumes some basic knowledge about our visualization technique. Due to the size limitation of videos, we cannot cover everything we wanted to. For the full story, please visit the CodeSwarm website to see the original videos The story of Python begins with Guido van Rossum, working alone in the late 1980s. He is Python's creator and benevolent dictator for life. A year later, 2 developers join him, but they stay on the periphery of the swarm. One of them, Jack Jansen, created MacPython. His activity stands out because his sphere of influence periodically converges and diverges with Guido's. Another person, Fred Drake, appears and commits mostly blue document files. Indeed, he will become the lead documenter of Python. This pattern of Guido being the clear central developer with specialists on the periphery continues. In the year 2000, the popularity of Python takes off. We see many new developers coming in as the project activity increases dramatically. And for the rest of the video, the project stays busy. The Eclipse project is vastly different than Python. Right away, there is a flurry of activity. Many developers working on many files at nearly a constant pace. This is possible because these people were already working on the same project before Eclipse was open sourced. We also see that, even amid the chaos, the Eclipse project is made of many components. There are many developers clustering around the center, yet they each have their own set of files. In other words, there is not one large set of files being worked on by everybody, but many small sets of files being worked on by individuals. This can be attributed to Eclipse's rich client platform, which facilitates modular design. Looking at the commit histogram, we see something not apparent in the Python video: weekends and holidays. Weekends are the periodic gaps in the histogram occurring every 7 days. The holidays can be seen at the end of December throughout the video. These breaks further reinforce the idea that Eclipse is developed with corporate sponsorship. This final video was not ready.
So this is not as important anymore. So what I'd like you to do is, again, look at maybe another video for one of the projects on the website and then discuss in your group these questions like who is the intended audience, what question does this visualization answer, what is the data represented, how is each data type encoded, and then why do you think this was a pretty popular visualization back when it was published. So I'll give you guys 5 minutes and then we'll talk about it in a group.
And I don't know what white stuff is. White stuff that like all this white blobs around me. So like just dots. Yeah. Like they come and go. So it said like the names stand out like when they're making a spell. Like they put shape around.
Okay, so let's talk about this. What's the data shown in this visualization? Names? I hear names. Like what names?
The developer names who were involved in.
Okay, that's correct. What else?
The code commit time.
The code commit time and how that's correct. What else? But what does the color mean?
What kind of files that were
File type, yes. What else? Time is encoded, yeah. What else?
The size of the contribution.
The size of the contribution. Anything else? What do the
The number of people involved.
Yes.
The frequency over time, how often per person commits.
It's true. What is how is position used here?
The mainstream ones are positioned as center, and then kind of the offshoots are towards the edges.
Yeah, so there's like the big ones, the main people and the main documents are in the center, and then there's other ones. But what's the relationship of the documents to the people?
I mean, the more number of comments and the more number of, interactions probably with that particular stream of work.
Yeah, so like what I'm trying to get at is that we have a person here, and the files that he or she is working on is on the circle around them, right? So the position is used to encode ownership of the documents. Okay, so position is used to encode ownership. Like we also had file type, that's encoded how? Color, correct? And then we had commit frequency. How is that encoded?
the blobs, white blobs.
Yeah, but is that frequency?
Histogram.
In the histogram, that's correct. It's not shown in this picture, but it was shown in the video. And it's also temporal, right? We have the appearance, so there's like the temporal aspect. So this is not a static visualization, it's not even an interactive visualization, this is really an animation in this particular case. So, can you read the data here precisely?
No.
So the only thing that we can read is usernames, right? And we have an idea about what types of files we have. But we can still say something about the visualization, right? We can still make inferences of the popularity of a project, about the structure. We can talk about the community, how they interconnect. We can also do inferences about the type of project, whether it's open source or commercial, as we saw in the video. So what do you think is like the value of this visualization? And why do you think, like, when they published this paper and put this tool online, It was really popular. It was around 2008, 2009. Why do you think that is?
You can compare and contrast community behavior for different projects.
Yeah. Other ideas? What's the value? Why people care? Would you care?
People were trying to see whether like corpus was like a good thing or bad.
Yeah. I think there's also a lot of like looking at your own pictures, right? You care mostly about what is the structure of your project and kind of like see stuff that you already know about in some way. So like my personal hypothesis why it's just popular is because people like to look at their projects and then compare it to other projects in the open source community. So who likes this visualization and wants to speak for it? Who dislikes it and wants to speak for it? Or against it? Nobody cares.
I don't like that there's no key or something telling you what the size of the circle means, what the XY axis means.
So it's very imprecise, right?
Yeah.
I agree to his point. I don't really like the graph because it's not really telling me much about what the visualization is. It's like there's a lot of things crammed down in one place and it's not really telling me what this is.
Yeah.
It looks good, more in artistic. It
Yeah,
looks
so
more like a painting, but
exactly. It's more like data art than actual like business intelligence, right?
It paints a big picture, but it doesn't tell me tiny important details like, okay, this person worked on this feature, or this feature was abandoned over time or something.
Yeah, but on the other hand, you could also argue that this might not have been the goal of the designer, right? And you could imagine a complementary visualization technique that allows you to do that.
Most of the time, I hardly see the names clearly.
Yeah, so there's problems with the layout algorithm, we have overlaps, there's label readability problems and so on. And so this is like a project by Kwon Duma and Michael Ogawa at UC Davis, and this is like falls into this space of organic visualization. And this is really more data art than like serious data visualization. I personally really enjoy that particular project. I also like the music for the video. But I think it tells an interesting story, it engages, it tells me something about, for example, Python that I didn't know, or about Eclipse that I didn't know. Of course, I wouldn't use it as like a GitHub built-in feature to report to management or on your productivity or something like that, right? There's better ways to do that. But I think there is place for these kinds of art projects simply because of user engagement and reader engagement. Anybody want to say something before we move on? Okay, so next I wanted to talk about data. So before we start with the data lecture, next week on Tuesday we will have a JavaScript and D3 intro. The next homework will be essentially like object-oriented ECMAScript 6 JavaScript with a little bit of D3. You'll be rendering like a very, very simple version of the tree of life. Then on Thursday actually, we'll talk about the visualization alphabet. So what are the things like color and position and so on that we can use to encode data. And what I also do for the first time is I will quiz you on our reading. And so this paper here, Crowdsourcing Graphical Perception Using Mechanical Turk to Assess Visualization Design, is like a new take on a seminal paper by Cleveland and McGill. It is kind of like a reanalysis of a perceptual study that was done like in, I think in the 70s. And you can learn a couple of interesting things about this. How do you run such a perceptual study? How do you use crowdsourcing to run such a study? But more importantly for this particular lecture, what are the differences between those visual marks? And so everybody here should really make sure that that you've read the paper, and I'll be like picking people randomly and ask questions, and then you can give answers, you can give summaries, and we'll be discussing this paper for 10 to 15 minutes. That's next Thursday. Okay, so data. In terms of terms, what are the different data set types and what are the different data types? So in terms of data set types, we have like tables, networks, fields, and geometry. And then for specializations for tables, we have like a flat table and a multi-dimensional table. And for networks, we have a lot of special cases, such as trees. And I'll go through those in more detail. And then the data types are these fundamental units that we use. And combinations of those make up the data set types. And these data types are not what you think of in terms of programming, like integers and floats, but it's more these like abstract concepts of items, attributes, links, positions, and grids. And so we'll go over those now. There is like a big difference between structured and unstructured data. Structured data has known data types and known semantics. Like in tables, we usually have a column that tells about what is in the cells below it. In networks, we're clearly distinguished between node and links. We have structure and so on. In unstructured data, we don't have a predefined data model. Things are, for example, text heavy, and text could be interspersed with facts, for example, dates, times, locations. Videos and images fall into this unstructured data category. And so what we usually do in visualization, we usually care about structured data primarily. We to some degree care about making unstructured data structured. I'll show a couple of examples. But mostly this is like the domain of things like natural language processing or image analysis or computer vision more generally to like essentially derive structure out of these unstructured data sets. So visualization by itself doesn't really concern it, is not really concerned with that. But even if you use some simple transformations, if you just use something very simple, you can derive some structure from unstructured data. So here, for example, we have the King James Bible visualized based on the pattern X begat Y. So they had a baby together. And just by using that particular rule, you can extract information, or not they had a baby, like X was the father or mother of Y. So these are parental relationships here. And just using this very simple pattern, we can actually extract structure from an unstructured source like the Bible. So here we can see Abraham is the father of Isaac, is the father of Jacob, and we have here Obed and Jesse and so on. And like here is a long line of people that are like offspring of each other. That's a very simple rule, but still we can, by simply using this in a smart way, we can extract some structure. So here is another pattern, XSY, like possessive relationship for 18th and 19th century novels. And I think I really like this example, that the wife is usually associated with some respectable person like an ambassador, an officer, or the father, whereas the bride is usually associated with the sailor, the outlaw, the freebooter, or the pirate. So we can see that those two terms like belongs together versus wife belongs to like the more respectable characters. Again, very simple, algorithmically pretty interesting, and we'll have a lecture on text and document visualization where we cover things like that. Okay, if we talk about data, we need also to talk about data semantics. So here we have like a data item, Basil 7S pair. What does it mean? What could it be? Like the name, the city, fruit, height, age, day of the month? It's not obvious, right? There's many different ways of thinking about what that data means. We just can't tell from just looking at the string. So here we have like an example of a table that has the structured and semantic information in the table header here. We have for Basil is the name, 7 is the age, shirt size is S, and the favorite fruit is the pear. So we need these semantics. We need this metadata to make sense of this data set. The data types are structural or mathematical interpretations of the data. Things like items, links, attributes, positions, and grids. And as I mentioned already, these are different from the data types in programming. So for example, a link could be a number, but could equally be a string, or could equally be a pointer. Right? There's many different ways of implementing a link. But still, conceptually, the way that, like, what I would like you to think about now is these data types that express some kind of like relationship. So items and attributes. The item is an individual entity, like something discrete. For example, a patient, a car, a stock, a city. And in statistics, that would often be called the independent variable. So, and the attribute is something that we measure about those items, something that we observe or that we log about them. So, for example, for a patient, the height, the blood pressure. For a car, the horsepower or the make. And these are often referred to as the dependent variable in statistics. So here is like an example of an item. This is the person. These are the attributes. Then in here we have the cell, and then on the left we have the identifiers. There's other data types. There's the links that express relationships between two items, like friendships on Facebook or follows on Twitter. It essentially captures like something between two items, a relationship which is important for graphs. Positions are important for spatial data that defines the location in 2D or 3D, like the pixels in a photo, the voxels in an MRI scan, or the latitude or longitude on a map. And the grids is something abstract that is the sampling strategy for continuous data. So, for example, how many voxels we have in an MRI scan, the position of weather stations across the US, and so on. So let's dig into those data set types a little bit. So for tables, we distinguish between flat tables and multi-dimensional tables. And flat tables have one item per row, and each column here is an attribute. And we have a unique key. And that unique key can be implicit. It could just be the position, like the index of the item or of the row. For the unique keys, and the flat table usually doesn't have any duplicates. And the unique keys, of course, are also unique. Multi-dimensional tables have indexing based on multiple keys. So let me give you specific examples. Here is again our flat table with an item, and here are the values. And then here we have explicit keys. And so these values are the attributes, keys and values together are the attributes, and the keys here are explicit. Here's an example of a multi-dimensional table. We have two different index structures. So here we have keys. These are patient identifiers from a cancer study. And then on the other dimension, we have genes. And that shows us the relationship between what is the value for this patient for this gene. So this is like a multi-dimensional table where we have two different keys in the table. So how can we visualize these kinds of multi-dimensional data? Well, we probably have about 2 lectures on table data visualization. But some simple examples here are parallel coordinates plots, or these kind of matrix plots where we have these circumcisers that show that. And graphs and networks are like the second big data type that we care about. And we'll have, of course, dedicated lectures to discuss graph visualization. Formally, a graph is a set of vertices, which are also called nodes, and a set of edges that connect these vertices. And so in your homework, you will be working with a tree, which is a special type of a graph. And the term graph and network, vertices and nodes, edges and links, they're mostly used interchangeably. If you use the word graph, you should say vertices and edges. If you use the word network, you should use node and link, but nobody really uses it consistently. And then like conceptually, like what I like to distinguish, but it's also not canonical, I'd say, graph is kind of the abstract concept of a graph, whereas network is a specific thing. So like I'm talking about graph theory or a graph algorithm, but I'm talking about the Facebook network. I wouldn't say the Facebook graph. Here are a couple of specialized definitions. Like a simple graph is a graph which contains no multi-edges or loops. So like every node is connected by no or a single edge. There's no 2 edges connecting a node, and there's no self-edges in a simple graph. Here are a couple of specialized graphs. The tree, in this like most loose definition, is a graph with no cycles. We'll talk more about trees. Usually you also assume some kind of root in the tree. A directed graph is a graph that distinguishes between edges A to B and B to A. And a hypergraph is a graph with edges connecting any number of vertices. So like one edge connecting up to like 2 to n vertices. And so that is more, you can also think of this as a relationship. So for example, like I belong, like me and all of these people that belong to this fitness club, we're all connected by one big hyper edge because we have this shared property. You can also think of this as a set on top of these networks. So hyper edges and sets are kind of very related concepts. Then we'll also encounter bipartite graphs. So bipartite graphs has vertices that can be partitioned into two independent sets, and there are no edges within those independent sets. So all of the edges connect, for example, in this example here, from a square to a circle. There's never a connection from a square to a square or from a circle to a circle. That's what a bipartite graph is. And these are kind of surprisingly important. And then there's other properties of graphs that we care about, things like an articulation point, which is a vertex. If we would delete it, it would make our connected graph into multiple graphs or unconnected graphs. So how can we visualize graphs? So there's the obvious classical visualization that everybody thinks about when we talk about graph visualization. These are node link diagrams where we represent the nodes as some kind of glyph and then the links as edges connecting those glyphs. Adjacency matrices, or matrices in general, are another important class of graph visualization techniques that we'll be talking about as well. And then tree maps are a form of implicit tree visualization. And so tree maps are great for certain tasks and certain types of data. And so here you already see a trend that not every visualization technique is equally valuable for every type of data set. So if you have a tree, not a graph, you can use a different visual encoding than you could use for a general graph. So fields are attribute values associated with cells. And these cells contain usually data from a continuous domain. So think about measuring temperature or pressure or wind velocity or rainfall across like a continuous field like we experience in our world. And these can either be measured or simulated. And so the big challenge here is sampling and interpolation, because if I measure them, I cannot like measure at every single point there is, right? I have to take some sampling points and then I have to make some interpolations of that. And that's kind of the domain of signal processing and statistics. An example that I like to use here is the air quality data like that we care about in Salt Lake City, because we have inversion events where we have better air quality. And so like these air quality predictions or even the measurements, they are based on very few measurements. Guess how many air quality sensors there are from like the official weather services in Salt Lake City? There's 2. And still, there's a lot of variation in the terrain, right? So if you're in the canyons, your weather or your air quality is going to be vastly different. So there's like a massive influence of topology, for example, or of smaller events in these fields. So this is a big challenge for working in these continuous domains. We distinguish between a couple of different grid types in fields. The simplest one is a uniform grid, where we can essentially compute the whole geometry and topology just by knowing the rules of the grid. A rectilinear grid is this one here, is a more like specialized case where we have non-uniform sampling, where we, for example, we could apply that if we know that we have something, like if we scan something and we know that this core of what we scan, we need higher resolution, but we want to save data and scan less, with less, let's say, resolution on the outsides. We can have structured grids, such as this here. Like there is some underlying rule between, to make this grid. This would be like, an example would be a curvilinear grid, or we could have something like a completely unstructured grid. This is a fully flexibility, but in this case we cannot infer any vertex and any connection. We have to store everything about this grid. You will, in practice, visualizing fields is not really the domain of this course. We will be talking about fields in the context of maps, but if you want to learn more about fields in the context of medical data, there is this new course which will be offered in the spring, Visualization for Data Science. And so that will focus on like what are the algorithms that I can use to make this efficient, things like transfer function, how can I use the same data set to show both the skeleton here and then the skin and the muscle structures and so on. And this is like this field this field of scientific visualization. So generally, like, at this point, I wanted to take a second to talk a little bit about these academic subfields of visualization. So what I'll be teaching here is mostly information visualization, therefore abstract data visualization, things like tables and graphs. And the nice thing about information visualization is, in most cases, we are free to choose our spatial layout. So it's a very creative thing, right? That's why we're talking so much about design. It's less about describing a reality. We can come up with whatever you like, whatever works well. The second field in academic visualization is called visual analytics, and that's a combination of information visualization, statistics, and machine learning. Those are like publishes a lot of applied work. I personally don't see too much of a distinction between those two. This is also mainly like a funding buzzword to like say we need intelligence analysis with visual analytics to stop a terrorist attack or something like that, and then you get lots of money. And then the third field that I just mentioned earlier is scientific visualization, where we talk about spatial data. And here you're not free to choose your spatial layout. What you have to do is you find the best way to depict the reality, to depict what you really care about. Things like not showing the skin but showing the muscles, not showing the muscles but showing the bones. All of these questions, which will be covered in the course. And so if you're not sure whether something is an information visualization or a scientific visualization, there is just like a very simple classifier. Whether the background is white, it's an information visualization. When the background is black, it's a scientific visualization. It's not precise, but it's probably the best classifier out there that you would find for that. And so these are actually Google searches, Google image searches for these terms, infovis and scivis. And there's of course like false positives, false values, but yeah. So the next data type that I wanted to talk about is geometry. And if we talk about geometry, we're talking about the shape of the items. Things like the shape of a county or a state or a country. So we'll be talking about this in the context of, for example, loading topo.json or GeoJSON file into D3. And this can be like, this is about explicit spatial positions, like points, of lines, of curves, of surfaces, of regions, of volumes. We will be using this as kind of like a background piece mostly. It's not really a core visualization topics. It's more important in computer graphics, or where you like want to have like big triangle meshes or CAD and so on. So we'll be touching on it for maps, but we won't be using geometry too much other than that. And then there's other data sets which are essentially collections. And we talked a little bit about sets. I like to distinguish between sets, lists, and clusters. We could talk that the distinction between clusters and sets is not completely unambiguous. But anyways, sets are unique items that don't have a predefined order, like in computer science context. Lists are ordered and allow duplicates, and clusters are groups of similar items that are not necessarily unique, at least in my definition, and that are not necessarily like discrete. So as a cluster could have like be a probabilistic cluster and so on. Whereas for a set, I am certain that something belongs to a set, like a club membership or things that are not ambiguous. Whereas clusters are usually something that I derive and like apply to a data set based on other attributes. Okay, so this is what I wanted to talk about data sets. Now let's talk about attribute types. Which classes of values and measurements are there? So there's the three main classes. There's these categorical nominal classes, the ordered categorical classes, and then quantitative types, attribute types. So what are the differences? Categorical or nominal, these two terms are kind of, it depends on there's different opinions, but nominal for sure is things like where you can compare equality, but otherwise not say much. Like you have things like types of fruit, genders, movie genres, file types. These are not necessarily orderable, and you cannot compare them by size or anything like that. But what you can do is you can compare if two items are of the same category. For ordered categories or ordinal data, there is a definition of size. So something like shirt size, X large versus medium, or the rankings. Like if you say number 1 bestseller, number 2 bestseller on the bestseller list, these are ordered, but if you have just this information, you don't know how much more book 1 sold than book 2, for example. And then there's quantitative data, where we can do arithmetic. We have things like length, weight, and count, where we can simply express relationships and do like all the math that we like. And for quantitative data, there's 2 subcategories. The one is interval data, when we have equal differences between successive points in a scale, but the position of 0 is arbitrary. So what I mean by that, like a good example for that is temperature, Celsius versus Fahrenheit. In both cases, the 0 point is somewhat arbitrary. Anecdotally, Fahrenheit was, the 0 point was defined as, like the guy, Fahrenheit, said, oh, it's a really cold day today, I can't really imagine another day to be as cold, so this is 0. Celsius at least has the freezing point of water at 0, and the boiling point of water, whereas like 100 Fahrenheit is like body temperature. So it's from some arbitrary low temperature to body temperature for 100 is the scale. So what is the problem here? Like it doesn't mean anything to say it's twice as warm today as it was yesterday, right? Like 100 degrees is not twice as warm as 50 degrees. There is simply no sense in making these kinds of expressions. Another example for these interval data is dates, especially years, or any date actually. So we have like a year 0 that is defined based on some historical event, but it's also not meaningful. So we can't really say we can't really do these kinds of arithmetics here. We can only talk about the differences, so the intervals. We can say something, it takes twice as long, but it's not, 2000 isn't twice as much a year as 1000. Quantitative data types are ratio data type. The most flexible data type is the ratio. Quantitative data type is the ratio data type, where we have real magnitudes of scores, and we have an absolute meaning for 0. So if we have the length of something, 0 means there is simply nothing here. If we have like a meter or a foot, we can simply make these relationships and do these calculations. So length, mass, age, weight, and so on. We can measure ratios and proportions of them. And this was all developed by Stevens in a science paper, and so he came up with these classifications between nominal, ordinal, interval, and ratio. And so just to repeat, and this is like a favorite exam question, data types. We have nominal, where we can do comparisons, like for equality or inequality. For ordinal data, we can do operations such as equality and inequality, or we can check for something is bigger or smaller than. For interval data, we can do all of that, all of the above, plus addition and subtraction, so we can measure distances. And for ratio data, we can also measure proportions, so we can do multiplications and divisions. Okay, so what are the type of variables for the following? The 50-meter race time. Ratio. That's correct. So we start at time 0, and then after 50 meters we've been run, we stop the time, and so this is clearly a ratio data set. College major? Nominal. Okay. Nobody has any illusions that computer science is inferior to math. My colleague always likes to say here that MIT actually numbers majors, so maybe they have a ranking. Amazon rating for a product? Ordinal. Yes, ordinal? The IQ score? I hear ratio and interval. What do you think it is? Too many people. Who thinks it's interval? Who thinks it's ratio? To those people who think it's ratio, what's like a 0 IQ? It's really hard to say something has 0 IQ, right? So the comparison I like to use here is, my cat doesn't score high on an IQ test. It probably gets a 0, but my fridge does too. Still, I would argue that my cat is smarter than my fridge. Okay, I'll continue this next time, and I'll see you guys on Tuesday for JavaScript and D3 introduction.